Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my video channel where I talk about everything that I want to that's math and science. And today we're talking about physical science, and we're going to talk about the atom, sort of what all of chemistry is based on, right? This is properties of atoms in the periodic table. So first of all, we'll talk about that where you find the elements. And what are elements? Elements are the smallest piece of matter that can be broken down and still retain the characteristics of whatever it is. So a gold atom, if you can see it under an electron microscope, would be shiny and yellow and look like gold. And if you could see I just showed my chemistry kids a video. It's on YouTube. And I think it's really good, and it's an hour long, and my students don't seem to think it's as terrific as I do, but it's called Atom's Ring of Truth, and I think it's by Dr. Philip Morrison, and in it, they get one element by itself, and I can't remember which one it is, but it's blue-green, a little blue-green ball at the very end, and so if you have one atom, it has the properties of the element. But if you break that atom down, they used to think the atoms couldn't be broken down, but they can. If you break it down, you get protons, electrons, and neutrons, basically. And we'll talk more about that. And they are not different from each other. All protons seem to be the same. All electrons seem to be the same. All neutrons seem to be the same. So that it no longer has the characteristics of what it is. So that's what the elements are. Where do you find them? You find them in the periodic table of the elements that is probably in the back of your book. And here is a book. Most science books have them in the back. Dun-dun-dun, the periodic table of the elements. The elements are represented by names, and then those names are written as shorthand. So like one kind of element is hydrogen, and its symbol is a capital H. Helium is another element that starts with H, but its symbol is capital H, lowercase e. And we're real picky about this because this is our language that can be understood universally by scientists all over the world. So we have to do it the same way. So helium is capital H, lowercase e, nothing else. Carbon is a capital C. We'll go this way for the thing, capital C. So, that is how it works. So that's what the symbols are. Now, so we talked about that atoms are made out of protons, neutrons, and electrons. The protons and neutrons are about the same size. They are stuck together in the nucleus or the center of the atom. Around the outside, there are tiny, way smaller electrons that zip around on the outside. And we'll talk more about what they do. Now, they used to think that the atom was the smallest. Then they found out about subatomic particles and started thinking that the proton, neutrons, and electrons were the smallest. But now, as we have learned more, we learned that there are even smaller particles that are like quarks and mesons and gluons, and there's a lot of other things that you can like major in physics just in those particles. And that's where a lot of our research right now in physics has to do with. That's a big undiscovered area. We're learning more. Every year you find out new things they've discovered, especially because now we have the Large Hadron Collider in Switzerland, and that we're learning a lot more about that. They're also doing stuff here in America, in the United States at the Fermi labs and the nuclear labs that are in Tennessee. So I've been reading about some interesting experiments. So anyway, fun things to read about and think about because it's so weird. It's so weird that it's really interesting. All right, so the atomic model has changed. So why is it a model? A model on something is not just like an Earth or, a model. I had a model of a frog where you can see you can open it up and see its guts for when I taught biology. But I think it broke, though. I think he had lost one paw and then another and flipper, and now he's broke. But anyway, that's a model. But a model in science is more than that. A model in science could be a way of explaining things or looking at things. So it is called the the atomic theory is a model of explaining atoms. And the reason why it's the atomic theory and not the atomic fact is because it's always changing. So we'll start at the very beginning. The very first mention that people have found of atoms goes back to a Greek philosopher named Democritus. And he was standing on a beach, and he said, this beach is one thing, a beach, but it's really made out of little bitty things, grains of sand. I am one thing. I wonder if I'm made out of little bitty grains like sand that don't break down. And so I'll call them atoms because atom means indivisible. So he did no experiments at all. He just thought about it and thought of atoms. And he was right. That's pretty smart, isn't it? Well, then came along sort of the dark days of chemistry, which were the alchemists. And they were kind of witches, a lot of like trying to do changing lead to gold, whether it's by science or spells. And so this is sort of the dark days that we don't talk about. And then it came to the modern era of chemistry that really started more in the 1700s. And the fathers of chemistry were like Anton Lavoisier. I'm probably saying his French name wrong, but I can say the other one, John Dalton. And these were people who started figuring out the first things about chemistry. And John Dalton came up with the atomic theory of matter, which is that atoms are what make things up. He named it after Democritus's idea. He could have called them Daltons. He called them atoms. And he said that he thought they would be like billiard balls that they would knock off of, they could bounce off of each other. And he pretty much figured it all out, what atoms were like. But he said that atoms could not be broken down. He didn't know about protons, neutrons, and electrons. So it wasn't complete. So it continues to change as we learn more and more about it. We don't throw it out. Just as we learn more, like, oh, there's subatomic particles, and then we just add that to it. And that's part of why it's the atomic theory of matter and not the atomic fact of matter. Not that it's not true, but that it's changing as we learn more about it. All right. So and a lot of times when technology leads science. So they had made the cathode ray tube. They could zap, they could make subatomic particle beams, didn't know what they were. And they started realizing that these beams could be deflected by or attracted because opposites attract and likes repel, and they could make the beam scooch one way or the other. So they started figuring out that this was some sort of subatomic particle, and that had a positive and negative characteristic to it. So then they figured out, okay, there's got to be subatomic particles, and J.J. Thompson came up with this idea that the atom was like plum pudding. And you know, it was a long time ago because that's not such a popular dessert now as it was back in the 1800s. And his idea was that it was like vanilla pudding if you put raisins in it. And the vanilla pudding would be the positive part of it, and the raisins would be the electrons. And that was what the atom was like pudding on the inside. And they knew it had a positive part and a negative part, and it was just like pudding. So then there was a guy named Rutherford, and he did an experiment to prove that J.J. Thompson's plum pudding model was correct. And what he did is he took gold foil. It's like tin foil or aluminum foil, but made out of gold, and gold can be beat much, much thinner, where it's just not very many atoms at all across. So just atoms thickness. And they took it and they shot the tube at it, the ray tube, and what they shot were positive particles called alpha particles. And when they shot it, what they expected was if you shot a gun at pudding, what would it look like? Splat, right? And they had this stuff that was like glow-in-the-dark stuff that would shine whenever it got hit with the splat. And so Rutherford, and they were going to prove that the plum pudding model was right. Rutherford was so confident that it was going to prove it that he wasn't even there when they did the experiment. His graduate students were there because you had to be in the dark room looking for the glow-in-the-dark splats, and that sounded boring and tedious, so he was like, you guys do it. Later, those graduate students became famous scientists too. But anyway, back on track. So what they found instead was that the the rays, instead of making a splat, it 99.9% of the time it was going straight through and hitting the same place over and over and over again. And every now and then it would be like it hit something and got deflected. And sometimes it would come straight back at them. The glow-in-the-dark thing was like a strip going around in a circle, and it was coming right back at them. They were absolutely shocked. Are you shocked as they were shocked? Why was this so shocking? Rutherford said it would have been no more shocking if he had taken a shotgun and shot a piece of tissue paper and the bullets come back and hit him. That's how shocked he was. Because what it proved is that the atom was empty space. My hand appears solid, but it's not. It's empty space. The only thing that's stopping this finger from going through that hand is energy, not matter. The atom is empty space. If this room that I'm in right now was an atom, the only part of it that would really have mass would be the nucleus, which would be as big as a dot printed on this book. Just a dot, a period, the dot of an I. It would be the nucleus. All the rest of the atom is empty space that's really held up by energy. The electrons orbiting around in energy levels is what gives matter its substance, not the matter itself. I always tell my students, but don't be discouraged. You always knew that there was more to you than the matter that makes you up. You're more important than that. Don't be discouraged finding out your empty space. You're important. All right. So then they came up with this idea, okay, plum pudding's out. So instead, it was the planetary model, that the nucleus was in the middle and that the electrons, they thought, and they realized that the nucleus was positive, because remember the ray tube was shooting alpha particles, which were positive, but the way it would shoot right back, they could tell likes were repelling. So they realized that the nucleus was positive, the little nut in the middle, the nucleus, and that they decided the electrons went around the outside, and they didn't know about neutrons at this point. Okay, and so they thought that was, and it would be like the planets orbiting the sun is what they thought it was like at first. And then they realized, they're probably not all in the same plane like the planets. And then it's what I think of as the Jimmy Neutron model. Whenever it was Jimmy Neutron, it would be this atom thing going in and out, and it was sort of like the planets going around the sun, but they're in all directions, and it was the electrons, and that's what they thought the atom was like. Well, then they figured out that was wrong. And it was Niels Bohr had a lot to do with this, and it's the quantum model of the atom, that the electrons hang out in energy levels and that they can hop up and down between these energy levels. It's not just one little oval like the Jimmy Neutron, that they can go in these orbitals where they can hang out in different energy levels, and that they fill the lowest energy level first. I might run out of power on this. I'll try to talk fast. Me touching that was low power, and I don't have it plugged in. Anyway. So, and then they also figured out that it's not smooth little orbitals the way the Jimmy Neutron model is, they hang out in clouds, and it's clouds of probability where you're going to find the electron. And that's the whole thing about Schrodinger's cat and the whole idea about the Heisenberg's uncertainty principle, that you can't know exactly where it is and its speed at the same time, because if you find out where it is, you have to stop it. So anyway, there's a whole lot of research to this, and you can learn a whole lot more in chemistry. So now, how are the electrons arranged on the periodic table? They're arranged by mass, and so hydrogen has the least mass. Originally, they were arranged by mass. Hydrogen has least, and then moving on up. And that was by a guy named Mendeleev, who told the elements where to go. Mendeleev, who put them down in columns in and rows. Mendeleev, who was willing, who was able to make a periodic table, who told the elements where to go. Everybody, Mendeleev! Okay, so Mendeleev was a Russian chemist, and he started discovering the periodic table. He discovered there were patterns in the elements, and he made the periodic table, but he did it by mass, how heavy they were, their weight to start with. Later, another guy came along, I think it was Henry Moseley, you might have to check me on that, who figured out that it's not the mass, it was the right periodic table is based on atomic number, which is the number of protons, the positive part of the nucleus that is in the nucleus. Later on, they figured out that there are some neutral parts that are just as big as the protons called neutrons, and those are also in the nucleus. What makes an atom is how many protons it has. So every hydrogen has 1, every helium has 2, etc. And that gives it its characteristic. Carbons have 6, nitrogens have 7. But they can have more or less neutrons, making them fat and thin, is how I think of them, which are called isotopes. They're different masses, and that gives them a little bit different characteristics. Like a lot of times when they have more neutrons, they become kind of too big for themselves and become atomically unstable, and they give off radiation. Like carbon-14 has got more neutrons, and it's the radioisotope, where carbon-12 has less neutrons, 2 less, and it is more stable. Okay? So we talked about isotopes. We talked about how you identify them. Well, you identify isotopes by their mass. Okay, the periodic table is organized in columns and rows. That was in my song. Okay, this is my little book I show for this. Hopefully we're not going to run out. Okay, it is a Sesame Street book. It says, the people in my family, and we have 2 families here, and if we were in class, I would read this book to you. But I'm trying to do this quick before the power goes out on my phone. But you will notice that these are families. On the periodic table, we have families too. And families have similar members. See, they both have a dad, they both have a mom, they both have kids. But the families are more alike than the dads are alike or the moms are alike. So this is what you remember in chemistry too. The families in the periodic table are the columns going up and down. They have similar members, but it's the families that have the same characteristics. So there's a family of the noble gases that don't really react with anything hardly. Then next to it is a family called the halogens, which make salts. The halogen are salt formers, and they disinfect. It's chlorine, fluorine, iodine, bromine. So then if you go over like to the other side where hydrogen is, you have a family that's very reactive in water. And they have similar properties. Even though they have similar members, they're more like their families. The rows going across are called the periods, and you'll learn a whole lot more about that in chemistry. All right, I think that's all we need to say about that. Let's see if there's atoms in the periodic table. Electron clouds, I told you about that. Rows and energy levels, I told you about that. Dot diagrams. So let's see if I want to do that. Okay, so when you look at the periodic table, the very first column, all of those elements have 1 electron in their outermost level. It's called the valence level. So they're all in the first column. They have 1 valence electron, and it can be represented by 1 dot next to their symbol. When I teach this in public school, I will give the kids Cheerios or M&Ms or something like that to represent the dots. The second column gets 2 dots. The middle part we skip because they do weird things. They're metals, they're kind of odd. But so you can see here, the first column gets 1 dot, they get 2 dots. We skip these that go down. And then over here they get 3 dots. And then over here, what they do is they have the ones over here get 8 dots. They're all filled up. They're happy octet rule. This is their noble gases, and what they all want is 8. And the ones next to them have 7, 6, 5, 4. That's how many dots you put around the symbols that represent the valence electrons, the outermost electrons. Why would we do this? Is because those valence electrons are the ones that do the chemistry. The electrons that are deep, close to the nucleus, they don't do anything. It's these ones on the outside that undergo chemical reactions, and by knowing how many dots it has, how many electrons it has, it gives us a clue to how it's going to bond and how it's going to react. So read over your chapter. Do the homework. If you're doing this as a class, do the labs I tell you to. Like, share, subscribe, and remember, science is great. See you next time.